The transition from an operational aircraft to a submerged wreck is usually violent and instantaneous. For Handley Page Halifax W1048, it followed a far stranger sequence. On the morning of April 28, 1942, the 30-ton bomber did not crash into Lake Hoklingen. It landed on top of it. The pilot officer Donald McIntyre, executed a wheels-up forced landing on the frozen surface of the lake. The aircraft came to rest intact, the crew evacuated. For the next 12 hours, the bomber remained where it had stopped, motionless on the frozen lake. But the loss was not over. Damage on the starboard side had already set a slower failure in motion, one that would only reveal itself hours later when the ice could no longer hold the bomber. This created a specific type of archaeological site. Most aviation wrecks are debris fields, shattered by high-velocity impact or exploded by ordnance. W1048 was different. It was a complete airframe, and it delivered to the bottom by gravity and hydrodynamics rather than kinetic destruction. It settled into the soft silt at a depth of 92 feet, disappearing from the surface world for 31 years. The identity of the aircraft is absolute. This is Halifax W1048, coded TL-S, known to its crew as S for sugar. It was part of No. 35 Squadron, launched on the first raid against the German battleship Tirpitz. It became a landmark Halifax recovery, a distinction that placed a heavy burden on the recovery engineering team. When local divers first found and marked the anomaly in 1971, they did not find a scattered pile of aluminum scraps. Later, Norwegian divers, including the Draugen Diving Club, would play a key role as the recovery effort took shape. What lay below was a ghost, the aircraft sitting upright on the lakebed, preserved by cold, oxygen-poor water. The recovery operation, launched in June 1973, was not a salvage job for scrap metal. It was a controlled retrieval, coordinated through Royal Air Force channels and carried out with museum preservation in mind. The objective was to bring the airframe back to the surface without breaking the structural continuity that had survived since 1942. The survey conducted by the RAF Sub-Aqua Association confirmed one critical fact. The landing gear was retracted for the recovery team, and that was physical evidence of a wheels-up landing on ice rather than a destructive impact sequence. On the lakebed, the environment is stable but hostile to movement. Visibility is low, the water's near freezing, and the bottom is made of fine silt and mud. This mud acted as a preservation cradle, sealing the lower fuselage from oxygen and preventing the rapid oxidation that destroys aluminum in salt water. However, this same mud now creates a significant engineering hurdle. The airframe is not just resting on the bottom, it is partially embedded. The suction force required to break the hull free from the silt is a calculated risk. Apply too much lift, and the structure might snap. Apply too little, and it remains stuck. The gap between the surface and the artifact is less than 100 feet, but it separates two preservation regimes. Below the thermocline, the skin can remain deceptively clean. Once the wreck is brought back into air, that balance ends immediately. Evaporation, oxygen, and drying begin a new cycle of change. The aircraft still appears coherent, but appearance is not the same as strength. 31 years of immersion have altered unseen load paths inside the wreck. The real question is no longer how W1048 survived the descent in 1942, but whether it can survive recovery in 1973. Halifax W1048 was lost in 2 stages, not 1. To understand why the aircraft still exists at all, the sequence of failures on April 28, 1942 has to be followed exactly. The aircraft was intercepted by anti-aircraft fire during its attack run. The starboard outer engine, one of 4 Rolls-Royce Merlin 20 power plants, took a direct hit. Nothing the crew did could bring the blaze under control. With the starboard wing burning and thrust becoming asymmetrical, pilot officer Donald McIntyre faced an immediate aerodynamic crisis. The aircraft could not maintain the altitude required to return to base. He was forced to trade potential energy for a controlled descent. McIntyre selected Lake Hoklingen as the landing zone. The surface was frozen solid. He made the critical decision to keep the landing gear retracted. A wheels-down landing on ice carries an unacceptable risk. The tires can punch through the surface or snag on irregularities, creating a pivot point that would flip the aircraft and destroy the fuselage. By landing with the wheels up, McIntyre maximized the contact area, distributing the impact load across the smooth aluminum skin of the belly. The bomber slid to a halt, structurally intact. The crew evacuated the aircraft, which remained stationary on the ice surface. This static phase lasted for 12 hours. This duration is the defining variable in the preservation of the wreck. The fire in the starboard outer engine continued to burn after the landing, and the heat did not simply dissipate into the cold air. It transferred via conduction into the ice sheet directly supporting the right wing. The mechanism of loss was a delayed failure of the ice, widely attributed to the ongoing fire but not pinned to a single proven cause. As the heat energy degraded the crystalline structure of the ice, the local thickness decreased. The load-bearing capacity of the surface dropped below the static weight of the heavy bomber. The ice did not shatter under impact. It melted until it could no longer support the mass. The aircraft slipped through the weakened surface and began its descent to the bottom. Because the aircraft went through a weakened hole in the ice rather than striking open water at speed, the descent was likely less violent than a typical crash. The airframe's later condition, largely intact on the bottom, is consistent with a comparatively gentle sinking and settling, not a catastrophic, at high-energy impact. This sequence also frames the primary anomaly found by the recovery team. The starboard outer engine was missing. Fire damage on the wing structure fixed the location of the blaze, but the exact moment and mechanism by which the engine separated was never confirmed. It was not recovered with the main airframe. The lakebed supplied the final preservative force. Instead of striking rock, the fuselage settled into deep, soft silt, which absorbed the last of the descent and sealed the lower structure in place. The silt preserved the aircraft's outward form, but it did not preserve every alloy equally. Fresh water spared W1048, the fast, obvious corrosion of the sea, while allowing a slower chemical threat to work deeper inside the structure. When the divers from the Royal Air Force Sub-Aqua Association first illuminated the fuselage of Halifax W1048, they encountered a contradiction. At a depth of 92 feet, but the aircraft did not look like a wreck that had been submerged for 31 years. The aluminum skin of the fuselage was bright, the rivets were tight, the paint on the roundels was visible. To the untrained eye, the bomber looked ready to fly. This visual evidence was deceptive. The preservation of the aluminum skin was a result of the specific chemistry of Lake Hoklingen. The cold, fresh water and the deep layer of silt created an anaerobic environment that starved the aluminum of the oxygen required for rapid corrosion. The metal had not oxidized, it had been pickled. However, an aircraft is not built from a single metal. It is an assembly of different alloys, each selected for specific mechanical properties, and each reacting differently to long-term immersion. The Halifax was not built from one metal. Alongside aluminum, it used magnesium alloys in a range of castings and fittings, parts chosen for weight and strength, but vulnerable to long immersion. Chemically, magnesium alloys can be highly reactive in wet environments, and on W1048, some of those components were found badly degraded. In the lake, those magnesium alloy components had slowly lost cohesion until some of the Halifax's normal hardpoints were no longer trustworthy solids at all. That material's failure changed the entire recovery premise. The trunnions and engine mounts could not be treated as lifting points because some had deteriorated into brittle, friable mass. The paradox of the site was absolute. The skin, which carries aerodynamic loads but not point loads, was pristine. The internal skeleton, designed to carry point loads, was chemically destroyed. The aircraft looked complete, but it was held together by geometry and the surrounding mud, as not by material strength. If the recovery team attempted to lift the Halifax by its standard maintenance points, the cables would shear right through the magnesium paste, ripping the wings off the fuselage. The corrosion trap extended to the control surfaces. The fabric covering on the ailerons and rudder had rotted away entirely, leaving only the metal framework exposed. But the real threat was hidden inside the wing roots. The bolts and joiners that transferred the lift from the wings to the fuselage were suspect. The team had to assume that the structural continuity of the main spar was compromised. This material assessment defined the primary constraint for the lift. The aircraft could not be pulled from the mud, it had to be cradled. Any force applied to the structure had to be distributed across the broad surface of the aluminum skin, bypassing the rotted magnesium nodes entirely. Whereas the divers were not lifting a rigid machine, they were lifting a fragile, articulated skeleton wrapped in a thin metal sheet. The plan required a lifting method that could spread the load over hundreds of square feet of surface area, rather than concentrating it on 4 hook points. The engineering challenge was to generate enough lift to break the suction of the silt without imposing a shear load that would snap the weakened spars. The solution did not come from heavy salvage machinery, those which could not be transported to the remote lake. It came from a calculation of simple displacement. The engineering solution to the recovery of Halifax W1048 had to be simple, portable, and scalable. Lake Hoklingen's rough terrain ruled out heavy industrial lifting gear, so the team built its buoyancy system from materials that could be carried in and assembled on site, a grid of 54 steel oil drums. Each drum had a capacity of 40 gallons. In the context of a 30-ton bomber, a 40-gallon drum appears insignificant, but the physics of recovery rely on cumulative displacement. The principle was simple. A submerged object displaces a volume of water equal to its own volume. If that object is lighter than the water it displaces, it floats. The Halifax was heavier than the water, especially with its interior filled with silt. To reverse the gravity load, the team had to attach enough external buoyancy to neutralize the weight of the airframe and, more importantly, for it to break the static friction of the mud. The process began on the surface. The divers prepared the drums by cutting the bottoms open or rigging valves for airlines. They then flooded the drums, allowing them to sink to the lakebed at 92 feet. Once on the bottom, the divers maneuvered the heavy steel cylinders into position around the aircraft. This was a manual operation performed in near-zero visibility. The placement of the drums was critical. Because many conventional hardpoints could not be trusted, the lift could not be concentrated. The drums were lashed into a web around the structure, secured to major spars, including wing and tail spars, so the force would spread rather than bite. The team built a cradle out of the water itself, using the buoyancy of the drums to support what had become a fragile geometry. The activation of the lift required a precise sequence. An air compressor on the surface fed hoses down to the drums. As the air entered the drums, it displaced the water inside. Each drum, when fully purged of water, provided approximately 330 pounds of lift. Multiplied by 54, the total potential lift force exceeded 8 tons. This was not enough to lift the aircraft entirely out of the water, but it was enough to make it neutrally buoyant. The most dangerous phase of the lift was the suction brake. The fuselage was embedded in the silt. The mud exerted a suction force that held the aircraft down, adding an unknown variable to the weight calculation. If the divers added too much air too quickly, the aircraft might suddenly break free from the mud. As it ascended, the air in the drums would expand due to the decreasing water pressure, increasing the buoyancy further. This positive feedback loop could cause the wreck to rocket to the surface, accelerating out of control and shattering upon breaching the surface. To prevent this, the team filled the drums in a staggered sequence. They pressurized the system slowly, watching for the first sign of movement. The goal was a controlled instability. They needed just enough lift to overcome the suction, but not enough to trigger a rapid ascent. On June 30th, 1973, the physics held. The suction broke. The Halifax rose gently from the lakebed, suspended in the water column by the grid of 54 drums. It hovered just below the surface, a ghost returning from the deep. The lift was successful, but the aircraft was now in a precarious state. It was floating, but it had no propulsion, and it was 3/4 of a mile from the recovery ramp. The transition from vertical lift to horizontal towing introduced a new set of hydrodynamic loads that the fragile airframe was never designed to withstand. The physics of the recovery changed the moment the aircraft began to move horizontally. Vertical lift had been a problem of buoyancy balance. Towing would be a problem of drag, stability, and patience as the wreck was guided beneath the surface toward the extraction point. The towing operation required a speed slow enough to prevent hydrodynamic drag from tearing the wings off the fuselage. The airframe, designed for flight at 200 knots, was now a high-drag object moving at walking pace. The divers swam alongside the wreck, monitoring the lashings and the stability of the drums. The transit was not just a movement of distance, it was a movement toward a structural threshold. At the shoreline, the environment presented a new constraint. The lakebed did not slope gently, it was soft mud that could swallow a heavy vehicle. To bridge the gap between the water and the solid ground, the recovery team utilized a piece of military hardware borrowed from the Norwegian Army. They laid down a temporary aluminum trackway, creating a rigid surface over the unstable mud. On top of this trackway, they constructed a wooden sledge. This was the critical interface. The aircraft could not simply be dragged up the ramp on its belly. The friction would destroy the fragile skin. The sledge acted as a mobile dry dock designed to cradle the fuselage and distribute the load. The divers maneuvered the floating aircraft over the submerged end of the trackway and settled it onto the wooden cradle. The haul-out phase initiated the most dangerous transition in the entire recovery. As towing lines tightened and the wooden sledge began to move up the aluminum trackway, the aircraft crossed the boundary from water to air. This moment was the point of maximum stress. In the water, buoyancy had supported every surface. On land, that support vanished. Gravity took over. The effective load rose sharply as the wreck left the water, and the fuselage was not empty. It carried years of wet silt. If the sledge had twisted, or if the belly had been allowed to point load against the trackway, the skin could have buckled under the dead weight inside. The team watched the structure as it broke the surface. Water drained away, but the mud remained. With bulldozers providing steady pull, the sledge held, and the degraded magnesium hardpoints were avoided. The load was carried by the skin and the cradle. By the end of the day, the Halifax W1048 was sitting on dry land for the first time since April 1942. It was intact. The recovery was a success of geometry and patience. However, as the water drained away, the aircraft was exposed to the atmosphere. The oxygen that had been absent for 3 decades was now rushing into the airframe, starting a chemical clock that the recovery team had to stop immediately. When visitors view Halifax W1048 today, the aircraft presents a visual anomaly. The aluminum skin does not reflect the polished silver finish of a standard museum display. Instead, it is coated in a dull, matte pink hue. This color is not a result of the fire in 1942, nor is it a stain from the 31 years spent in the silt. It is the permanent signature of the recovery's first conservation step. Upon breaching the surface, the airframe faced an immediate metallurgical threat: wet metal meeting oxygen. To slow that reaction, the recovery team sprayed the structure with a red-tinted corrosion inhibitor, using the color as a visible marker to confirm coverage. That protective coating, applied in urgency, not for aesthetics, left the aircraft with its lasting pink cast. The management of the artifact now demanded a choice that went beyond recovery engineering. In 1973, W1048 was the first Handley Page Halifax ever recovered from a crash site, and the only complete example then known. And that made the usual museum instinct obvious: rebuild it, straighten it, replace what was missing, and present it as whole. For W1048, the Royal Air Force Museum chose a different path. They elected to preserve the aircraft largely as it was recovered. This is the concept of as-found preservation, not erasing the wreck's story, but stabilizing it so the story remains readable. In that approach, distortions, missing components, and surface changes are not simply damage. They are part of the record. To rebuild the Halifax into a factory-new display would have required replacing original material and smoothing away evidence. Instead, the museum focused on stabilization. They created controlled conditions to slow deterioration, keeping the aircraft as close as possible to the state it was in at the moment of extraction. Today, W1048 is on display at the RAF Museum London in Hangar 5. It stands as one of only 3 complete Halifaxes in the world, and it is the only one that retains the unrestored geometry of its loss. It is not a simulation of a machine, it is a physical document of 2 distinct events: the crash in April 1942 and the engineering effort of June 1973. The recovery team did not just retrieve an airframe, they retrieved the specific conditions of its survival.